let's start the seminar. Okay, so we have 4 people. So the first one, I would like to ask Nikolai to solve the first one. Okay, the first one. But also people usually work with compact 3 or 4 and then define this quotient for compact 3 or 2. That's another approach.
I have to prove that this is a subgroup in the group of automorphisms of root system. Firstly, I would like to consider an isomorphism from G to G such that phi from H is H, and this is an isomorphism of Lie algebras, and understand how it acts on roots. Firstly, I would like to prove this simple lemma that phi preserves the Killing form. It is very simple because what is
phi actually? It's just some after.
it is yes, it is some automorphism that preserves H, and
that comes from this inclusion?
no, I would like to consider any such isomorphism. And firstly, I would like to prove that it preserves the Killing form. It is very simple because what is at phi z? It is acting on some W is this one, and it is because phi is an isomorphism of Lie algebras. So we conclude that this is and what is the Killing form? We should consider the adjugation of x and by x and y, but the conjugation by phi doesn't change the trace of an operator. So we have proved this lemma. The second observation is that phi induces bijection. It is bijection of sets. And to prove this, I would like to consider some alpha from X, from R. It is a weight. And what is phi H and phi x, where x in G alpha, it is phi from Hx, this is phi from this, and it is this. So I conclude that phi from x lies in G. This is standard notation. So we get that phi from x is a vector of this weight. And phi star, if we have phi from this to this, we have phi star which maps a covector f to the standard notation. And yes, it is just a dual operator.
Dual operator, there is no inverse.
I don't understand. We have an isomorphism, and this is an isomorphism.
In the definition of the dual operator, you have sense f, f composed with phi.
Excuse me. Yes. So I need to. Yes.
Just define this operator.
Yes.
Thank you.
And now.
May I ask a little question?
Yes.
Why it's from this computation we see that it saves the killing fault?
Yes. Probably I should expand this because. And on the next step, I would like to define what is H. I claim that H phi from this is simply this, and so I don't need I don't even need this because I can solve this problem in terms of H alphas or in terms of R. So I think that it is enough to solve it in terms of this, of R. And now we have a normalizer and how I can construct this map. If I have n from this, then I can consider Eden which maps from G to G and is an isomorphism, and it maps H to H. And
yeah, so it's actually at G restricted
yes.
to S.
And now I can consider at N restricted to H and consider this. So it, as we see before, maps R to R, and it is of course respects the Killing form, so it is an linear operator that respects an alpha beta that we defined before, because it respects the Killing form. And
I'm sorry, did we use already the fact that such phi respects the Killing form in here? Here I don't think so, right?
here we proved that
that phi inverse star induces
yes, and I can prove this with details, but now I would like on the first, if we trust in this, that this respects Killing form, so I have I would like to check that this is an isomorphism. Such thing maps to and this is and we use that taking -1 degree and star changes the order. So minus star changes the order and taking the star changes the order. So we change the order twice and get an homomorphism. And
I have a question. When you write R star, do you mean what do you mean? Is it just dual operator or coadjoint representation?
Dual operator. And now why? Of course.
N1 and N2 here are elements of H.
Yes. And we get an
From the Lee group.
Yep, what's written is confusing.
Yeah, and one too, it should be from the Lee group.
oh, excuse me. Yes. And what is the kernel of this map? Of course, the centralizer of H lies in the kernel, and if some map lies in the kernel, it preserves all roots, so it preserves all H. And because H is connected, it preserves H, big H.
So
It preserves all roots. So because all roots span H Gothic.
So H alpha span actually.
Yes, and we get that it preserves H Gothic, so it preserves H big.
What do you mean when you say preserve?
X-like identity.
But for algebra you should act by theorem, right?
Yeah.
No, so if I take some and it lies in 0, it means that this operator, each alpha maps to itself. But what this means, that it is an identity.
Yes, it's identity on H small.
On alpha.
Yes, on alpha.
Yes. Alpha spans H.
And then
H star.
Yes.
So take the dual and you get that the dual of this operator is then in degree -1 acts on H like identity. So it is identity.
I still don't understand. We need to find the kernel of this.
Yes, yes, yes. It is clear that C from H lies in the kernel. Is it clear?
Yes.
And in the other direction, if I have n in the kernel, I can write this.
Yes.
So do
I
you
agree that elements
do you agree with
of the kernel are
do you agree with this? From this we can conclude this.
Yeah, this is just the fact that the
Yes.
roots span and
Now
And H alpha spans.
right.
no, there
Yeah,
is
root,
the
root,
alpha.
root. Yeah, okay.
is it clear? Because we simply take the star
Yes, okay.
and but what this means that n acts on the conjugacy by n acts on H by identity
Yes.
on H star.
But we need to check that it's conjugation by it acts by identity on H beta.
Yes, yes, but it means so.
differential of conjugation is acting like
Uh,
the identity operator.
H is connected Lie group, so identity map and conjugation by n acts the same on Lie algebra of H, so they act the same on the whole Lie group because H is connected. So the
Is it true?
Yes, differential of an identity map is an identity.
Yes, but we need the inverse.
yes,
Yeah, the inverse is
we
only connected. Because you can, the differential is like the isomorphism between the small open subspace of 0 on the Lie algebra and small open subspace of 1 on the Lie group. And then you can span by this small open subset in the group. You can span all Lie subgroup because it's connected.
So
Otherwise,
for kinetic Lie algebras, the functor from Lie groups to Lie algebras is
oh yeah, it's also injected.
yes, it's faithful.
So that's also.
You can recover morphism by its differential.
Yes, by the exponent and the fact that the neighborhood of unity can generate the whole group.
Why adjoint operator of any n from normalizer saves h on its place? And it's not actually that h goes to the h, but why it's equal to the h?
No, I don't claim that the action of n
You claim
is identity.
like you say that it's isomorphism on h.
Yes,
So yeah, why so?
because do you agree that this is an isomorphism of G and it maps H to H because the conjugacy by n maps H to H. So, but
Oh, so the differential of its, yeah, okay.
because they have the same dimensions.
Actually, kind of. First, I wrote a matrix group, but I think you don't need the matrix.
Yeah,
for
what
that.
do you mean by matrix? Just the subgroup of JMN?
Yeah. So conjugation then is just conjugation, but by matrices, and you can kind of like see right away that it's inversible on acting on H. Therefore, we have it's actually isomorphism.
And what we what we need to prove that this is an isomorphism of root system. So we understood. It follows from this that it is a linear isomorphism, and we have to prove that it preserves these numbers.
And alpha.
But it morally it yes.
It is not.
What is not, what? Oh, this map from.
Is it exactly isomorphism? So this is Wellgroup, but the Wellgroup is not the whole isomorphism group.
Yeah, and how to see that this is a Wellgroup?
It's well, usually people start like if you go to books, there are different approaches. You can define it like as a something that is generated by S alpha, or you can start with such a thing, and then you prove that it is actually
S alpha generates
by
this, yeah.
reflections.
Okay.
I tried to look up maybe the other way, but usually it goes like that. Yeah. Okay.
Is there some interpretation of reflections in terms of this group?
Some particular elements here.
For example, for SLN we have bijection.
Yeah.
Explicit.
Okay, for SLN, for SLN you mean what? Which bijection?
So normalizer of diagonal matrices is matrices that permute basis vectors, right?
Yes.
And diagonal matrices. And then we quotient out diagonal matrices.
So it's exactly permutation group, which is wild group. So but yeah. So your question is there something like this in general case?
Yes.
Well, I guess you need to specify. You need kind of ad hoc kind of approach it here. You specify like what's Cartan's logic and how normalizer, what normalizers do. That's the only thing that comes to my mind. Maybe there is. Yeah. Okay. Okay. Number 2 then. Alex, you want to?
Yeah.
Number 2.
You already discussed it almost. So it's just expand the indices.
this group system just by permuting the indices here.
By EI you mean like the EII
Yeah, the matrix with the
with the 1 and
like
EE?
with 1 on
Yeah.
I and minus 1 on J. So,
Okay.
and we further claim
And
that
what is this EI minus EJ?
it's the root system.
So you
It's
identify
the root
diagonal
system with
matrices.
these diagonal matrices, yeah.
Okay.
And then the claim is that reflection in EI minus EJ.
Sorry, so you say that it acts by you just take a permutation, apply it to
Yes.
Y and J.
Yes.
Uh-huh.
Maybe I should run it. So it's then xi.
Isn't it's like 1ij should be strictly lesser than n? Yeah? It should be
No.
strictly lesser, isn't it?
No, because we have diagonal inside matrix.
No, it could be I.
Ah,
E,
yeah,
and
yeah, of course.
So yeah. So sigma maps this root to this root. And the way we prove it is to see that reflection.
So EI minus EJ is just it's from Cartan subalgebra, yeah?
From
Yeah.
X2.
The
You-
dual,
you
so
can-
that we can identify the root system with its dual.
Ah,
But
Oh,
we need
but-
to do it by killing form, right?
Yeah.
Yes, yes, with killing form.
Well, actually, if you identify it just by force, you'll get a 1 over 2n or something like that. I believe you get some coefficient there.
That's because you have one definition of dual with,
It's
so
not
another
killing.
definition where you just divide by this constant.
okay, it's not killing form, but some scalar
Yeah, you divide by this
rescaling.
number.
Like yeah, divide by 2n.
Yeah.
So it's trace. It's just usual trace form.
Yeah.
okay.
And then the reflection in this root we claim is just the transposition. Coefficient.
So it is an action in just Cn, right? So therefore it's an action on
Yes.
subspace for sure.
Yeah. But
okay.
but to see that it's actually a root isomorphism, we see that. So what we want to show is that reflection in EI minus EJ corresponds to the transposition. So the transposition IJ. If we can show this, then it's clear that it's on the reflections generate the heap of permutations, and then it's also clear that this is a root isomorphism. If we can show this, so we don't need to show that this is a root isomorphism.
Okay.
And so what we need to show is, say we take the I prime minus.
So this way you will prove, strictly speaking, that the Wellgroup is a quotient of the set, right?
This.
Because yeah, so you just need to also to say that this action is faithful, then it is a set.
Well, that the action is faithful is kind of.
It's kind of clear, yes.
This transposition is. Clearly they generate all of the set, and otherwise, so if we
Yeah,
have
why-
two different, permutations, clearly these maps would be different.
Yeah, you just check on this very.
We can
on
check
this
some
very
specific
vectors.
vectors where this map would be different. So
Right.
so it's clear we just have to prove this thing. So we have to look at what is reflection in EI minus EJ. So what happens if we reflect EI prime minus EJ prime EI minus EJ? Let's assume that I prime, J prime are all pairwise different. Then the claim is that when we reflect show that these two groups are orthogonal.
Where are primes? I just cannot see.
Okay,
So can you
I hate IG.
maybe KL?
KL,
Uh-huh.
KL, IJ are all gamma-7. So we just have to show that they are orthogonal so that nothing happens. So EK minus EL, EI minus EJ. So we look at the K form. And I don't think I have to. It's sort of clear when we have adjunction by EI minus EJ on some metrics. The only thing that will be left will be the IJth and the JIth corners. Then when we do adjunction by I and KL, if K and L are completely different, then
But again, you can
Then
just
we just
take
use-
trace for. So trace of this.
yeah.
Right. Maybe that's the same thing that you say.
Trace of
EI times EJ. This delta IJ maybe times something. I don't know.
Twice. 2n.
okay.
Maybe I think it's just like that.
Yeah.
Without any it's also this is also non-degenerate linear symmetric form, and the killing form actually is 2n times this.
Yeah.
Yeah, so you can also.
So they are orthogonal. So now we just have to prove the case where they share one index. So what happens if we reflect EH minus EI? What happens when we reflect this in the reflection of this root in say EJ minus EI? And now we can just look at A2 because we can consider A2 as the subgroup space of this root space.
Yes.
So we have just
I'm sorry. Why did you need orthogonality? This orthogonality.
because I wanted to show that when we reflect this root in EI minus EJ, nothing happens. So I wanted to prove
Yes.
that
Okay.
reflection in this.
And then you just take some where this is
I
intersect.
wanted
Okay.
to show this.
Yes. Okay.
That this reflection has transposition. So in the case that they share index, we can just look at the subgroup system A2. In minus 1, right? Yeah.
Yes.
Here everything is clear, so if we have EI minus EJ, now maybe I don't remember is it EI minus, I think it's EH minus EI, I don't remember if it's EI minus EH, but the point is that here is very clear what happens, we have reflection here.
But now you have two roots. I mean, two indices. One E1 minus. Three. I'm sorry.
Here when we make the reflection, we get EH minus EJ.
That's what we would like to check, right?
Yeah.
Okay. But maybe we just can say we have three indices. 1, 2, and 3.
Okay, 1, 2, and 3. And reflection in 1 maps 2 to 3, and reflection in 2 maps 1 to 3, and reflection in 3 maps 2 to 1. So it's clear here that we have just the group of this 3. This 3 group of permutations.
Yes, okay.
I just have to show that EK minus EL with when the reflection in EI minus EH is mapped. That EH minus EI and the reflection in EI EJ minus EI is mapped to EH minus EJ. And
Everybody agree? Okay. Yeah, thank you very much. Also, another way to solve this is to take a Wellgroup of SLM, and if acts, of course, on H star, right? But H star is inside D star, where D is all diagonal matrices in GLM.
Yeah.
And actually, you just kind of consider this as a hyperplane in here. And your action here will be exactly just transpose, permuting. Your action here is exactly permuting entries of vectors. Because now you have like EIIs, right? Not the differences like this, but exactly elements like this. So it's another way to see it. All right. So, okay, number 3 is about SO to n plus 1. Right? Number 3. Okay, who didn't talk for a lot of time? So maybe Anna, you can. In this homework, we kind of, please. In this homework, we kind of exhaust all rank 2 root systems. So we describe all Lie algebras with root systems corresponding to all ranks. So we have A1 union A1.
Where
What?
do we have A1?
No, this is kind of clear, but so this is the only things that was not clear is B2 and G2, right?
Okay, first we want to prove that this thing, our algebra is isomorphic to SL. Okay, this matrix define the symmetric bilinear form on the J line. So have group. And it is symmetric, so we have a basis when this matrix goes to the just identity symmetrics. So we have this thing is isomorphic to so we have our G, just a Lie algebra of this thing. You can yes, it goes to the so. Yes, so it's enough for
So
them.
does it goes?
we have when we take this basis, we move to this, so it also change this to this. So they are isomorphic too. Because this is just Lie
But so, yeah.
from G.
I would say it's the other way around. So if you, since you have a change of basis like that, so your change of basis you need for a linear kind of world, which is the algebras.
Yeah.
You can, by this change of basis, you can construct an isomorphism of the algebras, and from this it follows that this G is exactly O to n plus 1.
Yeah, just like I said, we firstly make the subgroups of Lie algebras or Lie groups.
Okay, so it is isomorphic because you have actually, linear non-degenerate map that sends B to I and plus
Yeah.
1, to I to n plus 1.
Yeah. Okay, but if we want to make the decomposition of H, okay, to find H, origin. So just diagonal lattices. Okay, firstly I want to make a view of our matrices here in G. It's
Sorry, why don't you complete the explicit isomorphism between these two Lie algebras?
well, you can just find this basis. It's not so hard to just like
But this transformation which sends I to B is B itself, right?
It looks like B squared is I n plus 1.
B square is I n, yes, yes.
like I think it's something like you need to change the basis like this for proper I and G, so it's something like that.
I think you need to add I somewhere. Because it needs to be some complex
Yeah,
change of coordinates,
yeah.
not real.
Yeah, but it's not so hard. Like, but this is a general fact that every symmetric matrix can be done like this.
Yeah, but
Every symmetric form.
the explicit
Believe
isomorphism between this one and SO to n plus 1 is just, so maybe the other way around, this X goes to Bx or, right? Is it Bx or Xb? I don't know.
I think it's XB.
Does it matter?
Yeah, it. Because, well,
So this one belongs to
Well, suppose approved with Bx.
this one belongs to SO to n plus 1. I mean, then this should belong to G,
Yeah.
right? So for X we have
the
what?
other way around then.
Bx.
Okay.
Bx, yeah.
Well, if
You can check that. Well, first of all, it's a linear isomorphism.
Okay.
I think it's easier to say if you have x from J, then it's
Well,
obvious that xb is from SO.
No, I think that's quite
This-
easy.
No, because you have
You
this
check
xb
that X
plus,
equals negative X transpose if you multiply by B,
yeah.
then you get
Yeah, you just get this.
something that satisfies this, right?
So
Yeah, so
That's
the
whole
question is, why is it actually Lie algebra homomorphism?
Yeah, you just prove, so your break is a commutator,
Yeah, okay.
so you just explicitly can check.
But can you do it?
Okay, let's try. Okay, maybe
I'll
I
do
can
it.
try that.
A little bit disconnected for a while.
Not because of curiosity, because I couldn't do it explicitly like this.
Okay. So maybe there is something that I overlooked. Okay, let's
Well, it's easy to see it's a linear map isomorphic, like it's an isomorphism of vector spaces.
yes. So yeah,
I did it on the basis essentially, but I don't really like it to be honest, because I had to like.
but just take
Do it on
x.
the basis, yeah.
I was trying to do show
We're
that
trying
this is
to show
isomorphism.
that if I take x and y from SO to n plus 1, right? And I take,
It will be equal to bx by.
so if I take an
Oh, b of x.
Well, you
like
need to
this,
write, yeah, this.
then
Okay,
it's,
so this is the isomorphism.
How to do it? Yeah, that's.
let me see.
Oh, that's quite.
So I have, so let's try to do it just straightforward way, right?
Do we really need this implicit form?
I don't think so.
Minus
But without it.
by
Because now
dx.
the text some solution that doesn't use it, I think.
Well,
Well, that's still interesting to know, right?
yeah. We want to know another solution.
Okay. So it should, you should have explicit.
So you need to take the basis, right? Because to prove it.
Guys.
Okay, so maybe not. Let's not do this. Let's do the root part.
Okay, so our matrix in G, they're like this form. And we have obviously basis. First, all ij will be larger than n. Second kind.
So now you are actually finding
That will be
the basis for your h.
yeah, it's just a basis in for these matrices, but also it's decomposition, root decomposition will be. So we need this guys. So this is just for A and D matrix. This for B, I think. These guys are for C. Yeah, and our H, they're spanned by Chita. Okay, I think it's the obvious part that the centralizer of H is H. Should we check it?
I think it should be clear after you actually
Yeah.
do like find all the eigenvalues.
So the result is I have.
And then we actually want to prove that it sounds logically stored, unless we never actually prove it. Of course, we just compute the basis.
Yeah, we just compute.
Yeah.
Yes.
There is no point if you have to find a root decomposition to do something else. Just fine.
Yeah.
Yeah. So the G. These kind of vectors and also we have these kind of vectors. And the third one, okay. And
alphas. Alpha I.
that's a name. It's just a name of.
Yeah, but you will write explicitly who they are, right?
Right now, yeah.
So maybe you can use another.
I can write it down here. It's enough space. But
Yeah, just let me erase this.
just don't want to go too far from that.
When you erase like this EN, EI, that was from the
Uh-huh.
group, yeah.
Okay, yes.
It's kind of hard to follow.
Well, okay. Have this. Well,
Sorry, do you really have minus in the second line?
yeah, because this is
No, the
like
second and the third one. It seems like you have the same here, right?
Somewhere should be some.
yeah, maybe I'm not sure about these computations, but yeah, wait a minute.
They should be. You would like them to be different, right?
Yeah, I think so. Yeah, maybe here should be with some.
Somewhere there should be some.
I think here, but we need to check it. Yeah.
Is it Kronecker symbol or?
Yeah, yeah.
I think here it's plus because in this. So what is your A?
No. Here is A, so I think plus is here. These
Right.
things are A.
Yeah, I understand. So what is there an explicit description of H in terms of blocks or like
Of
so
H?
these are diagonal matrices,
H spanned by this.
right? So they are matrices of the form X of H, whatever it's x1 xn, and then negative x1 negative xn, and then 0, like this.
Okay, so what's the question?
So I think that we should have plus here.
Why here? Why
Because
not
we have
here?
j plus n, so therefore,
Is it for the second basis, right?
yeah, for the second one.
Like second and third, and they're like common. They can't be so.
Yeah, also have plus as a second, but I'm not sure that this second is my second.
Well, it's just like this E is a matrix not identity, but just one on the place ij plus 1, right? And minus 1 on the place j I plus 1.
Yeah, so it's just in usual SLN, right? It will be this minus this.
Yeah.
So but it takes values from different.
Yeah, it should be plus.
So it should be plus.
Yeah.
Right. So actually we would like something like delta
agree.
IA
And the third?
minus
So here
plus,
will be
minus
minus.
plus,
Yeah.
delta.
Third one should be with minus.
Yeah,
Yeah,
minus
this,
minus. Yeah.
Something.
Yeah, third one should be
Yes.
with minuses.
Yeah, correct.
But you have.
I think we're missing something.
We are missing something, and this something is.
Yeah, we're missing the
The
first
last
one,
one,
right, with
yeah.
minuses.
If one of the coordinate is
Yeah, there this. I think this.
Yeah, so these are e's, and then there are
Minus
like roots. Yeah, yeah.
So
Which are F's.
one else.
with
That's what parents.
Yeah, this is, I think it's for the last
no,
row.
it's okay.
it was.
So you have here I greater than j, I less than j.
Ah, okay.
That's what we have. Yeah, but if we
No,
still
what
use-
I meant is that when you computed the basis, you kind of skipped the elements of the form that one of the coordinate is 2n plus 1.
2n plus 1, yeah.
Essentially,
Mm.
you didn't compute the basis of the part where you have x,
Mhm.
Yeah.
minus x.
Mhm.
So you need to
Yeah, I
add
forgot
these
this.
how many 2n elements to the basis.
Mhm.
Okay.
Yeah.
Mhm.
So we have also
And
this.
they
Yes.
should be of the form like.
This is important because this gives you like this special dot infinity diagram.
So it's not as 2n.
It is no
It
this
differs from S1 just by these things.
no it is SO2n plus 1.
Yeah, but if you erase YX and CY, then you will get
Yeah, then it
SO.
will be just SON and then you
Yeah,
Yes, you will get SO2n and this is D.
DN.
Yes. Right.
So we're done, or we correct this thing?
No. We do need
Okay.
Yeah, and for the fourth,
for this one.
for the fourth classes, we should also write the
Well, you need also
multiplication.
to
Yeah, yeah.
assume the fifth one. There are 5 different types.
What? The fifth one?
Yeah.
Yeah, but the fifth
The
one
fifth
should be
one
something like the
I
fourth one,
forgot.
not in the other way around, isn't it?
Now, so we consider e I to n plus 1, well, and to n plus 1 I. I don't believe it's actually even true.
Yeah,
It's not even
it's
an
not true.
element in this basis.
I think it's not even the element of this.
I think you
the
should
algebra.
write n plus I in the second index in the last. Oh my god, yeah,
Like
it's hard to talk.
Yeah, it should be something like e
What do you
I
want?
to n plus 1,
Короче,
e to n plus 1, n plus I.
Где, здесь или
Нет,
здесь?
внизу
Четвёртое.
v4.
Что?
v4.
Не, вот это.
А,
Короче, последний индекс не i, а n плюс 1.
n плюс i, да.
Мгм.
И там еще
Ну,
должен
потому
быть.
что у тебя y сдвинут чуть-чуть относительно.
а, да.
Ну и поэтому появляется еще 5.
Вот, и там еще пятый должен быть. Типа такого же.
А, да, если так и записываю туда.
Там должен быть.
Ну, потому что один дает...
Короче, вообще забыла про
плюсовые
эту строку.
значения, другой
Так.
минусовые.
Ну да, вот это вот для i, который меньше, чем n, а для i, который больше, чем n, там должно быть то же самое, только n минус i, но меньше.
Сойдем.
Должны, да.
У нас же 5
How many roots should we have? Not roots. Yeah. So yeah, we should have.
Like, we should have
n square minus n divided by 2.
like in
Окей.
Cartesian algebra we have n. Dimension of Cartesian algebra is n, and dimension of SO2 n plus 1 is something like 2n plus 1.
Times 10 times 2n over 2.
So we just need to subtract.
I mean, there is nothing wrong because we computed the basis essentially by just... So nothing can be wrong.
Ice.
If we have n equals to 1, then our algebra is just SO2, right?
SL3.
SL2.
Wait, if n equals to 1, it's something SO3, right? It's SO3.
Yes, SO3 is the same thing as SO2.
SO3.
Yes.
Probably you're right.
Yes. Yes. That's true.
So we need
Well-
one dimensional, right? It's okay. And we need 2 roots.
Well,
Plus
for n equal 1, that's some of this basis will be just zeros, because there's no,
Which will be 0?
well, I suppose like,
Yeah, because you should have I not equal to j in the first, I guess.
yeah.
I don't think it's yeah, it's not.
So in
In the first, yeah, you should I should not be equal
yes,
to
I
j.
should not be equal to j. Because otherwise.
Everywhere I
Yeah.
should not be equal.
No, wait. When I not equal to j, we have these guys. Why not?
Yeah.
But we find roots.
It's in the first one they can be equal, they are not. Yeah.
It will be just in Cartan if it's equal.
But it's not
Yeah.
a root vector.
Okay, yes. But it's still a basis vector. But in the second one, if I equal to j, it's not even a basis vector, I believe.
Actually,
Yeah, they're
so
in second, third we don't have
V4
I
and
and j.
V5 will be just minus, like it will be the same.
I think we have something like that, no?
Но еще point в том, что V2 он basis вектор только тогда, когда и не равно j, потому что если и равно j, это просто ноль.
Ну да. Ну да.
Вот. Поэтому с размерностью все равно.
Она просто половина 0, половина будут равны. Вот V4, V5 с точностью до знака минус,
Ну да.
V103 равны.
А внутри там есть сверху.
Не, V2.
P3, V2, да. Они одинаковые по строению. В смысле,
So okay, what do we have in the? So we have these two, right? But I can be, yeah, from
From
1
to m, yeah.
Yes. So therefore we have all guys like this as well, right? Delta AI. Yes. So for n equals 2, we have what? Right. So if I so if i's so if n equals to 2, right? Then my I and j and a. So a runs over the 1 and 2. So all of them run over 1 and 2, right? And so therefore we actually have in my root system the following vectors. So a kind of doesn't change me a vector because it's just a value on different elements of the Cartan, right? It's like it's components of the vector, right? A responsible for components of the vector. Yes. So I have something like so the vectors are like that, and then plus minus I e1 and plus minus e2. We just need to understand who is who here, right? So let me maybe.
yeah, actually, we don't need to understand anything now.
Yeah, you don't need to understand anything now. It's just let us just make it clear why. So all the values are like that, right? So index A corresponds to HA here, right? So therefore, when we're considering vectors, right? So index A is just index for component of the vector, right? In H star, right? So how do I? Right. So E1 in this case. Of HA is delta. Is delta 1A. So that's my definition of E1. If I have 2 here, then I have 2 here, and this is. So therefore, these are exactly the root vectors according to what Anna computed here. And you see, we have this picture, right? That they are like this.
Can we understand from this root system that you construct that the one vector is larger than the second one by 2?
By square root of 2.
Square root of 2, yeah.
Yeah, that's just clear from these are just so these are also orthogonal with respect to just what is induced by trace form, and then killing form is just some multiple of trace form. right? So these are orthogonal, so we just take them to be like, you know, the standard vectors, right? Standard basis in your R2, right? Then what I wrote here is exactly this way. So this is P1, this is C2, this is exactly P1 plus C2. Right? Yes.
I have some computational question.
Sure.
Is there any theorem which works for matrix subalgebras? I mean matrix Lie algebras, which are
Which are
prove that killing form, at least for simple ones, is proportional to trace of product, as we for a cell case, for a saw case, I guess it's true. I think.
Yes, it is true. So the question is, if suppose that okay, I consider this inside some GOV, right? On GOV I have non-degenerate form. If I restrict it, right, to my subalgebra, does it give me so it's invariant, of course. So the question is whether it's non-degenerate. It's not so clear. Just for any for simple. No, I don't know.
Okay.
So maybe not necessary. Да? Может вы нам расскажете? Ну, запишите. Okay, so then G2, do we have time? I hope.
If it will be such.
It will not be fast, no.
Yeah. So maybe let's take the most interesting Jacobi identity and check it. Yeah. So Leonid, maybe you can pick the most non-trivial Jacobi identity there and just check it. That's how. And or maybe what maybe we would like to see for the roots. What? Maybe Jacobi identity is not so interesting to check.
It's kind of.
It's interesting, but
It's
everybody can
small.
do this. Yes, but we really would like to see this picture, right? Okay, so maybe you
saw that.
Yeah, I saw that picture on the last.
yeah. Well, but who is who? Right. So maybe you can say who are the roots, like root subspaces, which are. I mean, ну вот кто эти коневые вектора вот здесь.
There's some natural construction for this algebra.
So there are papers, a lot of papers actually in G2, and I find this one to be the most natural. I mean, it is also derivations of factorials.
Okay, it's more natural.
More natural, yeah, sure.
Because this SLV kind of came out of nowhere, to be honest.
But suppose that you would like to create like something that has a root system that we have for G2. Right? Then I think you can come up with such a thing. So we have this, right? And you have also this. root subspaces according to the one sub from this. Okay. Yes.
From this part, have roots like this, and from this part, the negative part.
What is HII actually?
It's a matrix with one line as isolates.
And how it sits in V?
We just take a vector I and
The standard. It's standard.
but then this is just this. We know that Ekta's boundary graph is just all diagonal matrices from SLDs. Then we can say that this is just some element of diagonal.
Okay.
This is it. And here we have PI's transformed as root spaces. And clearly we obtain the picture of
Yeah,
So
it's just because we have dimension.
So actually we can
mean
put,
the number.
we can put roots in here. So if let me define the following functionals like this h1 h2 right is well actually it all happens in GO3 right is hi. So I have epsilon 1, epsilon 2 and epsilon 3. Right. So then my so what I got there the following. So if I did not sorry, yeah. So yeah, thank you. Yeah, let me just take. So alpha I is a usual roots, right? These are epsilon. So alpha 1 is epsilon 1 minus epsilon 2. Alpha 2 is epsilon 2 minus epsilon 3. And then alpha 3 is epsilon minus epsilon 3. So if I take right, so this picture is not very good. I would like this to be the long ones. And the long ones are those coming from SO3. Okay, and so I have alpha 1, alpha 2, alpha 3 like that. Right, but then I have the following, so epsilons are the other 3 roots. And so what I have is epsilon 1 here, negative epsilon 3 here, and epsilon 2 here. You can actually check, yeah.
Isn't for SL3 it's C2 and this is B2, isn't it?
This is
No, I mean the long one.
the long one is A3, is A2. So these are two A2s kind of together, the big one and the small one. So I actually can check that how you can actually got that these roots are like that. You take alpha 1, which is this one, right? And then I add epsilon. So I would like to see that I add some root 3 times and get alpha 2. Right? So this is so epsilon should be alpha 1 plus epsilon 2. Right? Which is so if I take what should I write? This one. So I take alpha 1 is epsilon 1 plus epsilon 2, which is negative epsilon 3, because the sum is 0. Then if I add one more time, I will get exactly this epsilon 2. So then there is only one this way. So to do this, and actually these three kind of, if I take like this half to be positive roots, which we will discuss today as positive roots, right? Then actually one of them is coming out of V star, not V. This is an interesting use, I think. All right, so let's finish on that. I have lecture in 5 minutes.
Вообще не знаю. У меня завтра колонка по Панкану, я вечером буду слушать про модельную структуру.
А в другом месте лекция? А в другом месте лекция?
Нет,
Все, что?
просто народ смотрел. Как оценки ставят только за семинары.
Ну, лекции же записывают, причем.
Кстати, крутой мув приходить за 5 минут до конца семинара.
Очень.
Надо будет сдать любой.
Мне как раз семинар Казаряна, например.
Прикольно,
И он как раз раньше
отвечали
заканчивает.
задачи, типа, и вы не рассказывать, потому что вы все рассказали. Типа, вообще кайф.
Или стабильно расскажешь последнюю задачу.
Решаешь одну. Ну, с другой стороны, да. Ты носишь должны как бы решить.
Ну да.
А чуть-чуть из функционал-то сложно. Все очевидно.
Да зачем вся эта хрень?
Что вначале? Покажи.
Про двойственность.
А,
Вот
ты
это
просто
что?
тоже не люблю.
Топологически индуктивный, двойственный, ну селективный. Почему?
Я помню, у меня все это было не очевидно, я там подробно выписывал все абстракты, все доказательства сертификата. По-моему, это следует вот отсюда.
Я вот как раз ты пришел, я доказательства выписал. Вот. Пункт 1.
Это как связано, да, вот с этим?
Да.
Нет? Просто?
Пункт 1 без этого получается.
Я забыл, что это топологическая индуктивность. Значит, что...
Гомеоморфизм на образ. Ну или эквивалентно, что норма не может уменьшиться больше, чем сколько грамм.
Это антиневичерность такая, да? Я не очень чувствую.
Все проблемы из того, что... Ты же знаешь, что такое объект категория, да? Все проблемы из того, что категория банных пространств не
А
объект.
это EB1, EB2, EB3, да?
Понятия не имею. Это где есть...
Где
есть прямые суммы, пределы конечные, конечные сопредел, ядра к ядра. И теорема об изоморфизме. Прямые суммы конечные.
То, что я знаю, это то, что любого морфизма есть ядро по ядру.
Да.
Это что есть эквалайзер, что есть непродукт, а да, есть конечный предел, конечно. А если есть коэквалайзер и непродукт, то непродукт одновременно и произведение.
Да, только он конечный прямые суммы.
Ну да, хорошо, конечные пределы есть.
определение сложения хомов.
Реально.
Ну, то есть не то, что хомы это обидвы группы, а там...
Он сказал, что это по-моему это.
Да. Но есть другое определение факториальное, что там есть какая-то... Есть диагональная...
Я, слава богу, этого давно...
Ну ладно.
То есть, скажем так, того, что пал, это вполне хватает, чтобы просто так вот обмазаться и сидеть, знаешь.
Ну, конечно.
У нас на прошлом семинаре у меня был сдача решения. Никто вообще, представляешь?
А что за задача-то?
Ну, на самом деле, у меня просто как-то мозг отключился, но это было нормально. Потом остальным было не знаю. Может, мы всех не знаем.
Я сейчас вспомнил, значит, есть, может быть, это тоже естественно, значит, реализация. Биту это что-то, значит, что-то, что сохраняет трилинейную форму, причем такую в общем положении на оси.
На чем?
На семимерной сессии.
Вот все-таки вот вопрос по поводу того, как доказать, что это отображение это марксизм и алгебра.
Ага.
Потому что альфа. Вот я не проверил на байс.
А я что-то даже не должен отправить.
Ну, то есть, я как бы это тоже решение свое не написал, но я отдельно честно проверил на байсе. Я как-то давно это делал для СВМ, аналогичная конструкция. Вот, а СВМ студент не смог, я такой, что проверил просто.
Мы это не используем вообще нигде.
Ну вот просто тут, да, тут как будто...
Мы просто...
Слушай, ну тут как бы трюк из разряда, я вам не буду рассказывать какое-то вообще отображение, да, вообще.
Нет,
Просто...
по-моему, все четко. Мы хотим представить другую реализацию.
Это совершенно изоморф. Я бы не построил изоморфизм.
Построили изоморфизм, но доказать, что он изоморфизм.
Да.
Ну да, нет.
А почему?
В решении не было вообще нужно даже строить сам изоморфизм.
Зачем тебе этот изоморфизм?
Изоморфизм получался из там, изоморфизмов Wellgroup. Да?
Нет, изоморфизм получался из того, что у нас вот эта форма, это то же самое, что форма, где все единички на диагонали.
Ну сказали, что если вот...
Ну, можно
сказать изоморф F,
да,
то изоморф F.
Вот. Мы просто поменяли базис пространства, и наша СОН превратилась вот в это.
Ну, типа, да.
Ну вот, я хотел вот именно конкретно показать, что вот это... То есть просто взять вот это вот...
А без базиса вообще не получается, там, если так вот коммутатор посчитать и воспользоваться этим условием.
Да,
определяющим.
потому что условие как бы добавляет сканирование матрицы, правда?
Ну да.
А в прямом условии его нет. Если там написать, можно...
Ну да.
Коммутатор 1 от 2 инфайнит b будет типа 1 от 2 b минус 2 а 1 b. А с другой стороны там будет типа 1 b от 2 b минус там от 2 b 1 b. Но и там b в центре выделивается. Его можно, конечно, куда-то убрать, а там, во-первых, он сократится с другим, да и сколько, а все равно b останется просто одной стороны.
Там типа B, если там на B, то это сканируется,
Это да, но это все равно не помогает. То есть, может, я просто не понимаю. Но вот, короче, я вот научился делать на базе. Просто не на базе, на базе.
Ну, собственно, базис явный это тот, который вот здесь типа выписался.
Я сначала, ну, как бы я проверил, что там есть изоморфизм, вот, нашел базис, дальше просто проверил, что это есть. Это прям такая вернадская работа. Когда есть 5 разных базисных элементов, ты получаешь
Нет, ну вот Николай же говорит, что проверяется.
Ну, там нужно какие-то типа замены базиса делать.
Ну. Okay, so let's start. Have a lot of cover because of bad lecture the last time. So hopefully this time this will be better. So let us start with a bunch of definitions. First of all, let us define regular element of. So again, our setting is that we have an Euclidean space, and we have a root system of this space. Okay, so what? So again, E is an Euclidean space. R some root system. So an element T of this Euclidean space is called regular if its a product with all roots is not 0. Definition number 2 is the following. A polarization of our root system is a decomposition like this into two parts, R plus and R minus. They do not intersect, such that R plus is all alphas in my R, such that alpha with T greater than 0, and R minus the same thing. Less than 0 for some regular T from E. So and R plus is called, so if we have a polarization, if you fix it, then R plus, elements of R plus called positive roots, and elements of R minus respectively negative roots. So elements of R plus are called positive, or R minus positive, respectively negative roots. So basically what you're doing is just drawing a hyperplane that does not contain any of roots. And on one side of this hyperplane, you will have positive root, and you choose on which side. And on the other side, negative. All right. So the next notion is what is a simple root. Simple root is positive, so alpha from our plus is called simple if it is not a sum of two positive roots. It depends, but not very strongly, right? So you can change t a lot. Once you change it once in such a way that it does not intersect hyperplane perpendicular to alpha. Then all polarizations will be the same. So yes. It depends on the choice of Weyl chamber that we're going to introduce, right? So if you take in different T's inside Weyl chamber, then the polarization is the same, actually. Okay, so this is this. So let us denote, so let pi capital denote the set of simple roots. Again, notice that it is inside R plus. No, when we say simple, it means that we chose polarization already, and we talk and when we say simple, it's positive by definition. Right. Okay, we have the following proposition. Proposition says that pi forms a basis for E. Pi is a basis of E. So let's prove this. So first, let us prove the completeness of pi. So that pi spans E. So it means that pi spans E. Yes. The idea is kind of clear that you take a root, positive root, and start, if it's not simple, try to, write it as a sum of two simples, and then if these two are not was that? Yeah, but you need to check that this is should be checked that this process is finite. Yes, but this is because of the following. So let T be right. But still, maybe you're going in circles. I don't know. So the goal is to prove that you're not. So let T be an element, a regular element such that alpha with T is greater than 0 for alpha in R plus, right? So let T be the regular element that kind of arises as a definition of R plus, right? Then actually, if I have some decomposition like this, where all alpha, alpha 1 and alpha 2, they are positive, this implies that alpha 1 with T is less than alpha with T, right? And alpha 2 with T is less than alpha with T. Right, just because all these numbers are positive and these two numbers are, sum of these two numbers is this number. Very well. So this actually says that this process that we would like to do is finite. Because let me take some beta from R. Well, from R plus, right? If it's not simple, right? So if beta is not in P, decompose it. Then if beta 1 or beta 2 are not simple, then decompose them again, and so on. And on each step, right, I will have this number like this, the inner product with T, smaller and smaller. And we have finite number of roots, right? So therefore, this process is finite. At some point, you will have simple roots. Yes, but you have a bunch of minimal elements. Actually, if you have, it's a good question. Maybe not even bunch if you have a regular element.
Well, I suppose you can have some of them be minimal.
Yeah. Just try.
Have some lexicographic order, right? The order on the side, you say that, let's say just these products.
No, if it is infinite, you have like some path, infinite path, where you have this number alpha with T, smaller and smaller and smaller and smaller and smaller. So this,
Finite numbers.
and only finite numbers. So therefore, so by this, decompose again, and so on. So by star, this process is finite. Therefore, any positive root is a sum of simple roots. And therefore, we are done because, well, because if you so R spans E, right? And if you got all R plus, then you just take negative of them, you get R minus as well. Right. So therefore, all roots from R plus is from R minus.
Why is this span R minus? Why is it?
No, I am saying that you can first create all R by sums and differences. Yeah. And then it get all E, of course, because R spans E. Yeah. So all roots from R plus are sums of roots from pi. So we are done, right? So completeness is proved. Okay, now yes.
So once again, is why is R minus is better?
Yeah. So R plus I can get as a linear combinations of pi's. Okay, then if so for any alpha from R plus, negative alpha is from R minus, and the other way around. So yeah. Right. So let's prove exists. Let's prove linear independence of positive roots. So 2.
So the fact of pi is E?
Yes, that's what we proved. Yeah, this is called completeness of pi. Yeah. So linear independence. Okay, so here we should just use that we know all root systems of rank 2. And this we use to show the following claim, that if I have 2 roots, which are simple roots, right, and they are different, then this inner product of them is negative, is actually non-positive, not positive. So this is because the following. So let me consider L alpha beta. So let this be the plane spanned by alpha and beta. Then if I take R and intersect it with L alpha beta, I claim that this is root system of rank 2 for L alpha beta. Root system of rank 2. You just can check all the parts from the definition of root system.
Did we choose a reduced root system?
Yes. Right, I should say this, that R is reduced. Right. So, therefore, but so now the claim follows from this fact for rank 2 systems. In rank 2 systems, you can just check by hand all 4 cases. Let us not do that, but for example, let's do our favorite example, which is not G2, but I think, do you want B2 or A2? D2? Yeah, D2 is clear. D2 is clear. Okay, A2. So you have this, right? And then you need to choose polarization. So let me draw this line here. So all roots which are to this side of this line are positive. And I see that this guy is, this is beta, this is alpha plus beta. So simple roots are these two, right? Therefore, and the angle is obtuse. So therefore, in this case, it's less than 0. It is 0 for D2. Okay. Now, we'll use this claim and to finish the proposition. So let alpha 1, alpha R be distinct simple roots. And suppose, by the sake of contradiction, they are linearly dependent. Suppose they are linearly dependent. Okay, then there exists some numbers Ci, I from 1 to R. Moreover, these numbers are positive, such that we have sum over Ci alpha I equals to sum over Cj alpha j. Here I runs over some subset I, and here j runs over some subset j, and intersection of these two subsets is nothing. So I just have linear dependence. All where I have negative coefficients, I just throw to the other side, and that's what happened. Okay, then let me now denote this vector as V, right? Then I would like to compute its the square of its norm, which should not be 0. It actually should be not non-negative, right? Should be positive, because 4 is positive definite. So I take this definition of V for the first entry, this definition of V for the second entry. So I will get sum over I from Ij from J, Ci, Cj, alpha I, alpha j. But these do not intersect, therefore this thing is less or equal than 0. Yes. These are positive, so therefore the whole thing is less or equal than 0. It's a contradiction. V is this vector.
Ah, okay, and we use it.
Yes, and this vector as well. Yes.
Why can't all the Ci? So it can happen that V is 0, right?
No.
Zero, then our linear combination is coming down.
And
No. We would like to say that suppose we have some linear dependence. Therefore, some of Ci's are not 0.
yes, some of the Ci's are not 0,
Yes.
but the vector is 0. So we have only one sign. For example, how do you obtain this Ci and Cj? You write in some linear combination.
Yes. So yes. Suppose that I have Ci alpha ai, right? Alpha I is 0, where sum of ai is not 0, right?
Yes.
So this is my linear dependence.
It can happen that all these ai are positive,
Right.
and we need to do something in this case.
So if all ai are positive, it means that
Well, I just take the smallest linear combination.
That's
The smallest amount of
yes, okay. So yes, we need to say something.
The scatter product with T.
No, I can't. No, wait. So you take the smallest possible linear combination that goes to 0.
Okay.
In case and then you take all numbers that are less than 0 to be one side.
Suppose that all are positive.
Yes, suppose that all.
Then you get, yes, then the product with T is just
Yes.
more than, and that's,
You're saying a alpha, ai. So this is v. No, sorry. Who is v?
yeah, I think you're just to prove that V is not 0, actually.
Yeah. So if I take this to be v, right? Yeah, so V and T, but we have, yes, this one is greater than 0, which is contradiction. Yes, thank you. All right. So we proved the proposition. Okay, so next definition that we need is Weil chamber. So a Weil chamber is a connected component of the following. I take E and throw away all hyperplanes orthogonal to my root system. So where L alpha is all vectors from E such that V alpha is 0. Okay, some simple proposition. So if we have polarization, okay, so fix a polarization. R is R plus union R minus, then C plus, which is defined like this. These are all vectors in E such that lambda with alpha is positive for all positive roots. Then this is a Weyl chamber. It's kind of clear, but right. So how to prove that? Well, since I fixed the polarization, right, I have some regular element. So first of all, if I take this C plus, it is connected. So I would like to, it's either, so I would like to see that it's not empty, right? It is connected because, well, you just take two points, connect them by line, straight line. You can see, like, yeah, it's convex, so this thing is convex. Yes, so we just need to check that it is not empty. And so proof, so C plus is connected. So we need to show that it is not empty. But if I take R plus, right, so if I have a polarization, I have some regular element that defines this polarization. So take, okay, I don't want to go lower than this, so. And this element will be in C plus. Yes, it's simple, but still worth mentioning. I mean, this is called the main Weyl chamber. So take T such that R plus is all alphas in R such that alpha T greater than 0, right? Then T will be in C plus, right?
Like Weyl chamber is any connected component?
Yes, yes.
So like when we have A1, there we have 6 connected. So
yes, yes. So we have these lines. So this is the main one. And then we have 6 others. But the main one is just because we chose this polarization. We have 6 other polarizations. So therefore we are done. So nothing to write here. So it is not empty because T is inside C plus. Okay, very good. So yeah, so it is connected, and inside the connect, it's either connected component or just empty thing. So we would like to see that it's not empty. So how we prove it? Since we chose some polarization, there is some non-zero non-zero regular element T, such that R plus is like that. Okay, and therefore such T satisfies this condition that we have for C plus. And therefore T is inside C plus, so C plus is not empty. Okay, so let's do, yeah, so another proposition, which is also should not be of a problem, the correspondence, so you take some polarization and get a Weyl chamber. So R plus defines some C plus is bijective. Proof. Well, first of all, it's surjective, right? So if I take some Weyl chamber, so surjectivity, I don't know, let's call it somehow C. I don't know. C is usually a category, but we don't have any categories here. Yeah.
We proved that it's a connected component of this thing, which is E without all hyperplanes, right?
Yes.
Why can it be smaller than Weyl chamber? I think some argument has to be made.
Smaller than connected component?
Well, like,
Smaller than,
yeah, like
it's connected, well, okay, it's not empty, well, it's also good.
for Weyl chamber, we did not say that it's whole, this part. We say that it's just some connected component of,
The connected component is yes, it's kind of maximal element of, yeah, so what should be said then? Yes, okay. We would like to see that it is not smaller. I mean, that's just, so the claim is that connected components of, so if I just take, so any Weyl chamber is just of the following form. These are T in E such that we have conditions like this. We have plus or minus here. Alpha T, right, is greater than 0 for all alpha from R plus. So I claim that all connected components of this E minus these planes are of this sort. Of course, so if you just consider any combinations of pluses and minuses, right, that it is either empty or a connected component, right? And this is just because, first of all, it's connected, and then they are disjoint, and they disjoint union of all these things actually. Yeah, it's the whole thing. So therefore, you just have that such things, it's either empty or a Weyl chamber with any combination of pluses or minuses here. So take all pluses. That's my definition of C plus. So it's either Weyl chamber or empty. So we proved that it's not empty. Okay. Good. So let's So surjectivity. So I take Weil chamber. And then I have an element T inside, so some non-zero element there. Then I claim, so all elements of Weil chambers are regular, right? So let me define polarization like that in natural way, right? So these are all alphas such that alpha with T greater than 0 for all, right? So I take C, define polarization like that. Then I claim that C of R plus is my C. Right? Should I say something more? So why? So if I take, so this kind of should be like a tautology, right? So but okay, so maybe in my notes I was convincing myself by this. So take this, right? It is a connected component containing T. Okay, just by definition. But this is exactly C, because C contains T. So this map works like that. Take R plus, take any T that defines R plus, and then take a connected component containing T. So that's our map. All right. But here we take C, take some T, and define R plus. So surjectivity we got. Injectivity, well, also you suppose that you have, I don't know, some C of R plus equals C of R plus tilde, and this is some C plus, the same one, right? Suppose this. Yes, just simple reflection.
Yeah,
yes.
Actually, just says that it's a bijection. Because all Weil chambers, we know how they look like. We just need to choose if it's minus or plus.
Yes.
And if you want to change something, just make a simple reflection.
You can do this, sure. Yeah, I guess so. But okay, let me finish since I do this, sure. So, let me now this. So let me take again the same thing. So let me take some T from C plus. Right. But anyways, from what I said, it's already clear, right? So how this map? So this is connected. No. We should do the other way around. So okay. Anyways, so then for R plus, right? It is what? So we have some T1, right? It's alpha in R such that alpha with T1 is greater than 0, and R plus tilde is kind of the same thing, but with some other T2, say. Right? But also we know that for if alpha is in R plus or in R minus, right? Alpha with T is greater than 0. Just because it's of how we obtained T plus. So therefore, in particular, R plus is inside. So this thing is inside this thing, right? But there is the same because, greater than 0 here, right? So this is R plus, and for each element of R plus, I say that alpha with T is greater than 0. So therefore, this is inside this, right? So, huh? No, that's how polarization is given. So I have one polarization, another polarization. So I have one T which defines this polarization for us, and another which defines this one. They may be different.
Didn't we show that if this polarization corresponds to C plus, then both T1 and T2 should be in C plus?
It's all simple here. I'm just everything that is said here is true, right? It's just which way you just need to follow one storyline here. So, right? Just to make sure that nothing wrong is said, right? So far it's okay, right? Yeah, so R plus is written like this for some T1. And for each element of alpha of R plus, we also have that alpha with T is greater than 0 because T is an element of C plus, and C plus is the main Weyl chamber for R plus. So therefore R plus is inside this set. So if this set is A, this set is B, we actually have, they are finite sets, and their sizes are equal, and this is actually a size of R over 2. Because we take a plane and divide it into halves. Right, so if I have roots, then this thing and some element, right? Then what is this set? It is half of roots. And this is also some other half of roots, but one is inside another.
Why one is inside another?
Okay, just because this is true for all elements of R plus. I don't know. Maybe not the best explanation, but.
I would just say that R plus is not equal to R plus.
No, so R plus equals to this set, and R tier the plus also equals to this set. So therefore they coincide. So injectivity. Yes. All right. So therefore we have this bijective correspondence. So next thing that would like to observe is that also, okay, this one let's call it lemma. So if C is Weyl chamber,
So we would like our Wellgroup to act on well chambers. And we would like to prove actually that this action is transitive. Okay, so but why does it act? Again, simple observation, if this is well chamber, then WC is a well chamber for some, or for any element in the Wellgroup. So this is why. Okay, proof. Again, I don't know. Maybe there is nothing to say here. So reflection is connected, is a continuous map, right? So therefore, connected component goes to connected component. On the other hand, of connected component of what? So we just need to check that union of hyperplanes goes to the union of hyperplanes. So it's a connected component goes to connected component of the same thing. Then we are done. But it's kind of clear, right, that union of hyperplanes. Root system goes to root system. So therefore, all these hyperplanes, union of hyperplanes, goes to a union of hyperplanes. So. But isomorphism of R, it doesn't mean that you have some transformation of E. I mean, isomorphism of so.
Isomorphism of R, we denotated that it's some isomorphism of E that says
Okay, yes,
yeah,
yes, that's true.
Yeah, but is it like continuous? Could it be?
Well, here I think we use
Linear map is continuous.
Oh, it's always linear.
Yeah.
So it's for any isomorphism.
Yeah.
Okay.
There is a problem that isomorphism can, so orthogonality can be not preserved by automorphism.
And what the problem?
When we define well chamber, we use orthogonality.
Yes, yes. So we need that a plane goes to some other plane. Yes.
To define L alpha.
Yes.
That's actually a good point.
Yes, yes.
About the group value inside of orthogonal.
So maybe not all of them.
Yeah.
Okay. All right. Yeah, so everything that I said is actually a proof of this lemma. So is continuous, and also union of L alpha as alpha is in R is invariant with respect to W. Mm-hmm. So next, so we have so W acts on a set of well chambers then, and the proposition is that this action is transitive. So the action of W on the set of well chambers is transitive. Proof. Right, so for this we will need a little bit more terminology. So we say that L alpha is a wall of some well chamber C. it's clear when, right? If I take the closure of C intersect with L alpha, and this will be some so let me formulate it like this: contains some open neighborhood of L alpha. No, not necessary. So think of so for A2, right, it's just half of L alpha. But the intersection itself is called face of C.
Don't understand. This intersection lies in L alpha.
Yes.
How can it contain neighborhood of L alpha?
No, it's not a line in L alpha. That's what I'm trying to say. It's some I don't know, something of dimension the same as L alpha inside L alpha.
So it's open in L alpha, right?
No, it's not open in L alpha. But so if you have, say, a line, right? So point is lies in L alpha, but it's not what we want. We would like something that looks like an interval or an array. We have actually we would like to have half a line in this case, right? So half a line intersect with L alpha contains some open neighborhood, say this one.
Open in L alpha.
Open in L alpha, yes, of course. Yes, sure. No, I mean, it's just maybe it's simpler than, I mean, it's harder to formulate than to understand. But I mean, sometimes there are some technicalities that are overlooked, and that's why you're here. Yeah, so you always look for mistakes. That's good. All right. So far, so good, right? So this is the face. And I would like to say that if some different well chambers share a face, and L1 is not equal to L2, C1 is not equal to C2, then let's call them are called adjacent. Yes. Where is it now? Okay, did we use it already? Yes, this one we used. So let's go back to here. So now we would like to make the following claim. What's that?
What is share face?
So they too have. So if face, if they have common face. That's it.
But that face, we determine the face with alpha.
Yes.
Or with the union.
No. So suppose they have wall. So for example, like again in SL3, right? So you have this well chamber, right? I should take another. So this well chamber right, is adjacent to this one. So they share a face. But for example, this one and this one, they are not adjacent, but they share a wall, but not a face.
But this two faces.
What's that?
Yeah.
Yes. Each well chamber has two faces, but in different ranks, they will have more. Yeah. So these two adjacent, these two adjacent. Yeah. So claim that I would like to do is that suppose I have two well chambers. Then, so claim, okay, it will be claim 1 actually. So let C and C prime be two different, maybe not even different, well chambers. Actually, yeah. Then there exists a sequence of well chambers. The first one is maybe the 0th one is C, and then you have C1, C2, and the last one, CK, is C prime. Such that CI and CI plus 1 are adjacent. Proof. So I take T and T prime, these are elements of C and C prime, respectively. And then the idea is to find the path. So T is inside C, T prime is inside C prime. And consider a path gamma from T to T prime such that if it intersects hyperplane L alpha, then at the point of intersection, right, there's no, it's not a point of intersection with our plane. Okay, so we can actually do this. So let me write this down. So such that yeah, so we would like to find a sequence of
but why exists?
yeah, because if you so because L alpha, they intersect in dimension 1 less, so you can move your path a little bit to the side and avoid this point. So that's the idea.
So like if you can take just a line, but
Yes, yes. You deform it, and then you get what you need. So what I need, how to write it down from this path. So such that if gamma of S belongs to some hyperplane, right, for some alpha in R, then this point is not in L beta for all beta in R minus plus minus alpha. Hopefully I got it all correct. What I would like to say, right? So, and again, you just take if you get such a point, you just can deform it a little bit and have and satisfy this condition. Yes, but also you can consider as you know, on each hyperplane, the intersections. They give you dimension dimension 1 or less, you know, lines inside hyperplanes inside L alpha. So that's why you can do this. All right. So and then my C then take C0 and so on, Ck to be all Weyl chambers such that gamma goes like through this CIs, right? So it intersects CIs, and it is actually intersects CIs in the corresponding order. So first C0, yes, and then C1, C2, and so on, in the corresponding order. And so then we are done. So all the CIs are adjacent. CI adjacent with CI plus 1, right? Because we just intersect one hyperplane when we go from CI to CI plus 1. And so we are done. So claim 1 is proved, and claim 2 is the following. So let C and C prime maybe I don't even so let C and C prime be adjacent. Then C prime is just S alpha applied to C for some alpha in R. Okay, so proof of this. Again, these are some exercises in Kirillov actually. So how would I do this exercise? So if I just take this is another Weyl chamber, right? So let me denote this. So denote C1 to be S alpha C. I mean, it's not even what I want. Right? So be adjacent such that the common face belongs to some L alpha. Right, then I have this.
How can it be?
Hmm?
How can it be not so? That common face doesn't belong to an alpha.
No, that's how. That's my. So suppose they are adjacent. That's my just definition of alpha.
Belongs to L.
Yeah.
We fixed alpha.
Yeah. So I just take not some alpha here, but I specify which exactly alpha I would like to take. So I denote C1 to be this, but then if I take its closure, it will be S alpha.
Isn't it just obvious because alpha obviously maps it to some chamber, and there are only two chambers that have this alpha as common face?
Right. That's exactly. It's almost everything here is obvious. You just need to write something on the board. Right. So what I would like to say that C1 is this, right? But C bar has face which belongs to L alpha, right? But S alpha just it doesn't move. It doesn't move L alpha at all for all x from L alpha, right? So therefore, this guy also have face. So therefore, C1.
What is C bar?
It's a closure, right? So this thing, right? So therefore, C1 has face L alpha intersect with C bar. But C1 does not equal to C, right? Because, well, for obvious reasons. So therefore, C1 is adjacent to C, but there's only two well chambers adjacent with a common face which belongs to this particular L alpha, right? So therefore, C1 equals to C prime, and that's it. So now from these two claims, we actually have the proposition. Where was the proposition? So the action is transitive, right? So what do? I take two while chambers, and then I make a sequence of adjacent ones, and then they are all related by action of some S alpha. And so therefore, the two that I started with are related to an action of some element of Wellgroup, right? So by claim 1 and claim 2, we have, so for any C and C prime while chambers, we have C prime is S alpha 1, S alpha 2, and so on, S alpha, I don't know, K applied to C prime. And so we're done, right? For some alpha 1, alpha K from R. And so we have.
Somewhere we shouldn't be right.
Yeah. Maybe not. Maybe here. And we have corollary saying that if I have if I have two different choices of simple roots, then they are related by an action of a Wellgroup. So for two different choices, pi and pi prime, of simple roots, we have pi prime is W of pi for some element of Wellgroup. So actually we have two different polarizations, R plus and R plus prime. And once you fix polarization, you actually already fix simple roots, right? So maybe proof is that let R plus prime be such that so R plus contains pi, R plus prime contains pi prime, right? Then let us denote. So we know that we have bijective correspondence between, right, to be C plus and C of R plus prime to be C, maybe without even C prime. All right. Then there exists some element of Wellgroup such that C prime is WC, right? That we proved because of the transitivity of the action. But then I claim that R plus prime is W of R plus. Is that clear? Should be. Something should be said, right? So again, let me take T. Right, is from C, regular element which belongs to C. So take T from C, right? Then WT will be in C prime, right? Then maybe the other way around, right? Yeah, so C is, if I take T from, right, so this way, okay, we're good. So now, then R plus is prime is a connected component containing WT, right? So this is by definition is alpha from R such that alpha WT is greater than 0, right? But this is the same as W alpha, right, from R, such that alpha and T is greater than 0. Reflection doesn't, sequence of reflections doesn't change us the form. Right, so therefore we use this, but this is exactly what? W R plus. Very well. So also W is linear, so therefore it sends simple roots to simple roots. So therefore W of pi is exactly pi prime. Yes, so we proved this corollary. I think we're, so please tell me the time. -5 minutes, that's okay, better this time. Yeah, so next, so our goal is the following. So we would like to classify kind of all root systems, reduced root systems. But for that, we would like to find some smaller set, which is simple roots. And maybe use that to classify. So then we have two questions. So can we reproduce a root system out of simple roots? And how two different choices of simple roots can differ such that they correspond to the same root system? So we answer the second question. And the first question is actually not so far away for answering. Yes. Ну да.
Будут задачки.
Да.
Наши камеры веера называются, да, по-моему?
Да.
Они же, получается, образуют веер. Веер.
Ну что это такое?
Ну вот то, что происходит, это, собственно, и веер. Ну, полный веер дальше.
Что такое веер вообще?
Веер — это объединение выпуклых конусов, которые там пересекаются, как-то не пересекаться должны. Ну, то есть,
Эти штуки не пересекаются вообще.
да, не пересекаются.
Нет, не пересекается.
В общем, там какой-то набор свойств есть. Ну вот, а у нас прям хороший такой веер, который все заполняет и не пересекается. Вот вопрос в том, ну, логичный вопрос, соответствует ли ему какой-то многогранник?
Да, соответствует. Но сейчас я не уверен, что соответствие один в один, это надо еще подумать.
Вряд ли один в один.
Но это все связано с этими, с кристаллическими группами Кокстера. Вот, то есть, вот, например, на плоскости вот эти 4 случая соответствуют 4 возможным многогранникам, которые отражением от собственных граней могут заполнить все двумерное пространство. Вот если вы захотите придумать вот, возможные, там с точностью до рескейлинга, конечно, то их вот будет как раз 4 случая. Это будет как раз многогранник, натянутый на фундаментальные веса. Вот мы их еще будем рассматривать. Вот он такой получается.
Сейчас, там насчет первой проблемы, насчет существования пути, там, мне кажется, какие-то более сильные условия в смысле.
Что?
Ну, непонятно, почему так будет существовать в плане.
А что может быть плохого? Нет, ну мы можем эту точку обойти, как бы, я не знаю, как это лучше сказать.
Верится, что там такое существует, но в смысле, что...
А в чем проблема? Вроде доказали.
Что надо? Нет, на лекции мы...
Это нельзя доказать как-нибудь вот примерно таким вот способом, чтобы вообще не говорить про эти пути какие-то?
Можно,
Вот,
я думаю, что можно.
У нас есть